the chair of the IEEE AP MTT Malaysia Joint Chapter. So we have 3 societies that join for our chapter in Malaysia. I'm also as the Dean of the Faculty of Electronic Engineering Technology, UNIMAP, University of Malaysia Perlis, as one of the co-organizers for this event. Thank you very much, Dr. Nasir, for having your time to present or to share a very interesting topic on spacecraft antennas. I have met Dr. Nasir, I think a long time ago, probably 12 years ago during our PhD times. I think when we attended this antenna human body interaction ESOA short course, I think that time. So we spent 1 week together over there in France. But anyway, I purposely messaged him through LinkedIn because we saw him share a lot of session with all the expert or interest parties in the world. So I think we want to get his also expert and sharing session with Malaysian as well. But anyway, we received a lot of registered participants. I think almost around 160. Most probably they will join in as soon as possible. Before that, maybe I can share. I would like to mention about his biography. Dr. Nasir received the master degree in electrical engineering from École Supérieure Ingénieurs de Rons, if I pronounce it correctly, and then PhD degree in signal processing and telecommunication from the IETR, France. Since then, he has been working with NASA, Jet Propulsion Laboratory, acting as the senior antenna or microwave engineer. And then since 2013, he has been also as a technical section staff and product delivery manager. He has authored and co-authored more than 100 technical journals and conference papers. Also wrote a textbook entitled Cubesat Antenna Design. And then I think a lot of his invention and for this Mars mission, the world first interplanetary Cubesat. Dr. Shahad also the recipient of 2011 CST University Publication Award, Best Paper Award from Bioinformatics Society, IEEE Antenna Propagation Society, Doctoral Research Award. I think a lot of award for his PhD thesis. And last but not least, in 2020, he received the IEEE Outstanding Engineer of the Year from IEEE Region 6. A lot of achievement, Dr. Nasir, for your valuable contribution to the society. And I think now I would like to pass to you. Now the floor is yours. Thank you very much.
Thank you for the invitation. It's my pleasure to be here. So today I will be talking about innovative antennas for interplanetary mission and Earth science missions, work that I've been doing with my colleagues for the past 10 years. Second, I will show the slides. Okay, so I will be covering different missions, including the most recent that most people who are following what's happening in the world of space exploration will be very well aware of. It's a Mars helicopter. Then I will talk about the Europa Lender mission concept, which is also a very, very interesting mission concept, where we had to develop new antenna technology to make it possible. And I will also cover a bunch of antenna technologies for CubeSats and ongoing research on future technologies. So we'll start with Mars helicopter. So Mars helicopter is actually a crazy idea that was proposed in roughly around 2014 is when we got started quite heavily to develop this technology. At the time, people thought that this mission was not possible for a very, very good reason. We have never flown, we've never done a powered flight in another planet other than Earth, obviously. And we actually started with the hardest one of the hardest one, which is Mars. The reason why it's one of the hardest one is because the air density on Mars is only 1% of Earth's air density, which makes it even very, very hard to actually create lift. The gravity is actually helping us a lot because it's 1/3 of Earth's gravity. So the mass is 1/3 of the one on Earth, so that helps us. So even though we have less lift being generated, the mass is slightly lower. However, the density, like I said, is only 1%. And the ratio of mass is 1/3, so we still have a big difference. So to make this happen, we had to keep the helicopter extremely low mass, and we also had to design an helicopter that's efficient in terms of power and generating lift to fly on Mars. So we designed a helicopter, or actually the team designed a helicopter that had the rotors, the blades as large as possible to fit under the rover, because this helicopter was carried with the Perseverance rover. So it had to fit under the belly of the rover. So the blades are roughly 1.2 meter, which is more or less the span of your arm if you open up your arm like this. And then we also had to increase the rotation of the blades, the spin rate of the blades. So to give you an idea, on Earth, the spin rate is around 400 RPM in average. For Mars helicopter, we had to increase to 2,400 RPM. And obviously, we're limited in terms of power, embedded power. So all of the subsystem, instrument sensors, and telecom subsystem had to be low consumption, as low as possible, because we are constrained, because we're getting the power from the solar panel. We have to recharge almost every day, actually every day. And we're also limited in the area of the solar panel. So I'll show you a little bit more about the design of the helicopter, but I will emphasize on the telecommunication subsystem design because this is my contribution to this project. So you can see on the left actually what the helicopter looks like. So the solar rays are very, very clearly shown on the top. So it's this rectangular shape with all of the solar cells. And in the center of it, you can actually see a monopole antenna, which is what we use to communicate with the rover on the surface of Mars. Under the solar panel, you can actually see on the bottom two rotors, so 4 blades, and they are turning in different directions. This is what we call a coaxial helicopter. This is the concept that the team decided to go with because that's actually the most efficient. So the blades that's on top is actually compressing the air density so that the blades on the bottom generates more lift. That's how the concept of the helicopter works, the coaxial helicopter works. Under that, you can actually see a cube. This cube is basically imitating the format of a Cubesat, so it's almost 10 by 10 by 10 centimeter cube. And you can see that it's actually covered by MLI for thermal purpose, so that the electronic inside during the cold night can survive. And obviously, on top of that, we also have heater that will heat all of the subsystem that cannot survive the very, very cold night on Mars. So, and that's where the power budget is also very important, because we need to have sufficient power to actually fly, but we also need to have enough remaining power to survive the cold nights. And then you have 4 legs that obviously allows us to land smoothly on the surface of Mars. Yeah, that's about it. Oh, one very important thing about the helicopter that we learned as we were developing the telecom subsystem, and that's very important for antenna engineers as well, actually mainly for antenna engineers. The solar panel is actually made of carbon fiber filled with foam. Carbon fiber at UHF, we're operating at 914 megahertz, is actually a very good reflector. So we use the carbon fiber as a reflective surface for the monopole antenna. So it's basically a ground plane. And the blades that you can see that are fairly large, they're also made the same way. They are made of a shell of carbon fiber filled with foam. The reason why they are made this way, it's actually to keep the mass of the helicopter as low as possible. So just so you understand how light these things are, the first time I was put these blades on my arm, I was asked to close my eyes, and they put it on my arm, and I could barely actually feel the blade's weight on my arm. That's how light these things are. And it was very important to ensure that we could fly on the surface of Mars. And as a result, every other subsystem were given mass constraints as well. The helicopter telecom subsystem was given only 13 gram, 13 gram, which is quite drastic, nothing like we've done before. That includes the antenna, the coaxial cable between the antenna and the radio, and that also includes the radio and the connectors, obviously, to connect everything together. That's very, very low. And to give you a comparison, a Cubesat, an interplanetary Cubesat, Marco, that we'll talk about, it had a radio that was more than 1 kilogram. I think it was 1.5 kilogram or so. So that gives you an order of comparison. So we had to do things completely differently. We had to rely on commercial radios. So we actually used the Zigbee radio operating at 900 megahertz, 914 megahertz to be exact. So we did a lot of testing. We modified the radio to actually be able to survive the launch where you have a lot of vibration, and also survive the flight to Mars where you can have very hot and cold temperature. So you have a big swing of temperature range, so thermal shock. And you also need to survive the landing on Mars where you have the impact on the surface of Mars, and also whenever you have a pyro that opens up, it generates shock. So all of that had to be taken into account, and we had to make changes on the radio. We had to design very carefully the antenna from scratch to ensure that we could survive all of that. So the main goals of the helicopter were actually it was a technology demonstration. We were lucky enough to be added to the to the Mars rover in Perseverance. And it was not part of the plan initially, so there was a very late accommodation that had to be made, which made our life very difficult in terms of design. I'll give some of the insight on that. Like I said, the helicopter had to be fabricated light but strong, limited to 1.8 kilogram total for the entire helicopter. The helicopter had to be powerful enough to lift in the thin Mars atmosphere. And the helicopter was designed to make flight of up to 90 seconds. And we actually went way beyond that in the different flight demonstration that we performed on Mars. And obviously also a very, very important point, the helicopter had to be designed to fly on its own. So as most of you know, there is a delay between Earth and Mars. We have an orbiter orbiting around Mars that the ground station send a set of command to. But because of the distance between Mars and Earth, we will not get the signal fast enough to be able to do a real-time control. So the signal will be received within 15 minutes to 20 minutes, depending on the distance of Mars, which varies over time. So that's a very important point. Imagine that you're driving your car and you were not able to react within 15 minutes. So that's basically what the helicopter had to do. So it was designed with a bunch of sensors. It had an altimeter to know exactly the height, the elevation of the helicopter or the altitude of the helicopter. It has a gyro, which tells us what speed we're going out, and also what the inclination of the helicopter. So all of this information are very, very important. We also have a navigation camera, and all of that combined, the navigation team is able to tell us exactly at what speed we're going, in which direction we're moving, and they are able to tell the helicopter, if we tell the helicopter, you need to do a flight at 5-meter height, and you need to go 200-meter away and come back at the same point, the navigation control is capable of doing that. So that's a very, very neat feature that the helicopter has that was very important to actually be self-sufficient on the surface of Mars to perform this flight that are pre-commanded with a set of commands. Okay. Okay, so let's talk about the helicopter antenna first. So you can see that the helicopter antenna on the picture where I show an exploded view of it, it's a monopole antenna. The gap between the ground plane and the radiating element is kept with a PCB board, which is made of Arlon 85N. And on the bottom, we have a very tiny GPPO connector that feeds this antenna itself. So the PCB design had to be done in a fashion that we can actually connect this connector and that will excite the radiating element, and we'll always have contact between the PCB board top surface, which connects to the radiating element at all time, even when we have a change in temperature. So that had to be designed very carefully, and we did a lot of tests over thermal to ensure that there is nothing that disconnects when we have a big swing of temperature. So we did a test going from very cold to very hot, and we didn't see any difference, which confirmed that the design was very robust. As you can see in the design, we have this pigtail here. It's because we were limited in height because we had to fit under the rover. We were giving a certain height that did not allow us to have a quarter wavelength. So as a result, we had to add this pigtail to compensate for the inductive effect of reducing the length of the monopole. And like I said earlier, we used the solar panel as a reflective surface or as a ground plane. And as you can expect, since the ground plane is not symmetrical, as you can see on the top right, obviously your cross polarization is not going to be perfect the entire in the entire directions. So 360. And that's what you see here. So if you had an infinite ground plane, you will have a cross pole that will be extremely low, close to infinite if you had an ideal monopole. But here, because the ground plane is not symmetrical, you see these cross polarization spikes in different directions. So that's caused by the ground plane. Then on top of that, if you had the blades, which as I explained earlier, are made of carbon fiber, they are reflective, then you more. And the pattern that I show on the bottom right is basically a real-time pattern as the blade is rotating. So I'm showing every 15-degree increment, how the cross-pole is being affected. And obviously, you can be in directions where the cross-pole is very, very small, so the polarization loss will be close to zero. Or you can be in this worst-case scenario where the cross-pole and the copole are overlapping. So in that case, you will have very, very high polarization loss if the rover antenna polarization is not ideal either. So you can actually see on the left a GIF that shows you how the blades are rotating, and that's what you need to keep in mind, is that the radiation pattern of the antenna will evolve as the blades are rotating as well. So then we were given an allocation or a volume in the on the rover, and we didn't have a word on where we wanted to be. Actually, as a matter of fact, we were told you stick to this area there, and you have to make it work, because we will not be able to make any other accommodation, otherwise it will affect the design of the rover too drastically. And at the time when we started in 2014, the Mars helicopter was just a demonstration, and we were not given the green light to proceed as part of the rover. So as a result, the rover was giving us accommodations that were not helping us, but were helping them in case the helicopter will not be included in the Mars 2020 mission, rover mission, which everyone thought would probably not be included, because the demonstrating that the helicopter could actually fly on the Mars environment was close to impossible. So everyone was assuming that we would fail, and as a result, they would have to remove it before flying. So that's the reason why we got the worst spot on the rover, which is shown right here, and you can actually see here on the rover as well. So if you put two things, the location is not ideal, so you're going to have reflections that will impact your radiation pattern. It will impact your cross polarization and your copolarization as well. And you will also have shadowing effect that will occur because you have the big mast and head of the rover is on the way. You also have the UHF antenna that's right behind the helicopter base station antenna. You have a lot of things on the way. You also have the AGA on this side as well. So it makes things very, very difficult. So as a result, we just, and then on top of that, on top of the non-ideal location, we also were given a very, very tiny ground plane. So as you can see, the ground plane is even smaller than the monopole itself. So it's smaller than quarter wavelength. So this is why you obtain this radiation pattern that I show on the right, where you have the vertical polarization in blue, which is the copole, and in red, which is the cross polarization, the horizontal polarization. Okay. So we did a lot of analysis to predict the radiation pattern of the helicopter and also of the rover base station, which I showed before earlier. And then we did a bunch of link budget analysis to predict what data rate we will be able to achieve and within what direction around the rover. So the plots that I show here, let's focus on one. Let's focus on the one on the left. The rover will be at the center, so at the center of these plots. Then there is a radius of 250 meter diameter, and around that there is another circle that shows a 1 kilometer radius. So initially we were given the constraints of never getting within this 250 meter zone, which we call the keep out zone around the rover, because we did not want to put the rover at risk. So we wanted to ensure that the helicopter would be sufficiently far enough that it would never crash onto the rover. So that was one of the most important requirements. And then we wanted to be able to communicate at a range of up to 1 kilometer so that we have enough flexibility to fly in any direction and around the rover. Obviously, because of the non-ideal locations that were given for the base station, it was not easy to do that. And as you can see the plots here, I have 3 plots. The first one is the ideal case. So each of them are statistical link budget. So the one on the left is the ideal case. The one in the center is the average case. So in most cases, we will be in this scenario. And the one on the right is when everything is worst case. So when we have the blades that are aligned in such a way that the Mars helicopter will antenna pattern will be the worst when we have the copal and copal that are overlapping. So the polarization loss will be the worst. And also the direction where the helicopter is oriented toward the rover will also be the worst. So that's how we plot. We obviously, when we do a telecommunication link budget, we never design for the worst case because otherwise we would be spending an insane amount of money to actually close the worst case scenario, which statistically is very unlikely to happen. And there is a way to avoid being in this case as well. So here in this case, we will just rotate the blade again, and then we will randomly be in another case where we will probably be in an ideal or average scenario. So those are the things that we need to keep in mind when we design a telecommunication subsystem. So the radio was tested to know what receive power is required to ensure the 250 kilobit per second data rate. And same thing for the 20 kilobit per second. Afterward, we added the feature of 10 kilobit per second. So that was added up much later in the game. So I'm not plotting here, but it's a 3 dB difference. So those are what the color means. So the dark green is 250 kilobit per second, light green is 20 kilobit per second, and white means we don't have link. So basically, looking at these plots, we will be able to communicate within 250 kilometers in most cases. And within 1 kilometer, there are directions where we might struggle, so we can make recommendation to the rover to be in a certain direction to be able to close the link if we are at distances as high as 1 kilometer. So that's why these plots are very important. So one thing I forgot to mention about these plots, they are when we are on the ground. So the helicopter would be on the ground in this case. And so when the helicopter is on the ground, the link is actually much more difficult to close because we have multipass, because we're so close from the ground, we have multipass, and the propagation loss is actually much worse than when we're flying, which is closer to free space. And this is the case where we are actually flying. And so as you can see, when we're flying, we have no problem at all. We can close in any direction in most cases. Yeah, so this case is actually pretty straightforward. We can close the link at 250 kilobit per second within 1 kilometer in most cases. And same obviously for 20 kilobit per second. So we actually did not, because we were so constrained in terms of budget, because it's a technology demonstration, we took a lot of shortcuts. We did not measure the radiation pattern of the antenna. We just measure S11 for the antenna. So we mainly relied on the fabrication process of the antenna to know that there won't be any issue. And we did S11 measurement on the base station and the Mars helicopter antenna as well to make sure that everything was behaving the way we wanted. And for to ensure that the link budget, the propagation loss, the antenna performance were as predicted. We did test on the EM using a Rover mockup with a breadboard antenna for the base station on the Rover. And you can see we also have a mock-up of the helicopter, and we have same thing, a breadboard on the solar panel, where we actually use this carbon fiber solar panel. We didn't have the cell of the solar panel, but that was good enough for the purpose of the test. And we actually did a field test where we separated the rover and the helicopter. They were at a distance of 200 meters, if I recall properly. And we actually had the rover on this structure, and we actually rotated the rover 10 degrees at a time to verify that the rover pattern was as predicted. In every direction, we always found that the receive power was never worse than the worst case we predicted, which is what we expect. And in most cases, we were either better or very close to the average prediction that I was discussing about earlier. And this is the plot that you see where we have the angle around the rover. So we go from 0 to 360. And as you can see, the three plots that I show, which are predicted, are the three cases that I was describing earlier. So the ideal, the average, and the worst case. Okay, and now that we have flown on Mars successfully, now we're at the 9th successful flight. Initially, the mission was planned to be 30 days only, but we've been so successful that it was extended. It's been going on for more than 3 months, I believe now. We were planning to do up to 5 flights, even though the baseline was 3 flights. We're now at 9 flights, successful flights. So I'm going to show you some of the comparison between calculation and measurements for different cases. So here, what I did was comparing the received signal when we were on the floor at the beginning of the flight. And that's the one you see here, where the received power was around minus 51 dBm. No, sorry. The measured received power on Mars was minus 49 dBm, and the calculated, predicted received power was minus 51 dBm. So we have only a 2 dBm difference, which is quite impressive. And during flight, at I think I took this value at the center. I mean, in midway of the flight, the measured was minus 37 dBm, and we calculated minus 39, almost minus 40 dBm. And when we landed, also we have a very good accuracy again. This is the plot is versus time. So when we landed, we actually came back at the same position. So the helicopter took off at 3 meters, flown for, I think it was 100 meters, came back, and then landed on the same spot. So yeah. So that was the first flight. And then I wanted to show you a comparison during 2 other flights, the flight 4 and flight 5, which were much more interesting because the distance between the rover and the helicopter started to be significantly higher. The first flight were actually very close range. But as we became much more knowledgeable on the behavior of the helicopter and verified that everything behaved as expected, we decided to take more risks, so go even higher in altitude and go even farther in distance. So this one was 260 meters at an altitude of 5 meters. And what I'm showing here is actually this flight was taking off, going on one distance, coming back and landing on the same spot. And you can see the plot. So the predicts are the same, obviously, because the trajectory was exactly the same, one way forward and backward was exactly the same. But the actual measurement on Mars were actually slightly different because at each moment of a time where the helicopter was making the measurements, the blades were in different directions. So the behavior of the antenna was different. So you could have more or less losses, polarization losses that would explain these differences. But as you can see, overall, the predictions are actually very, very good. So we were very happy to see that. Flight 4, actually, you can see a nice animation here that shows the image recorded. So these images were actually taken during the flight. They were recorded. And after the helicopter actually landed, the helicopter sent back all of these images, and we put the images together to make this nice video together. So you can actually see the helicopter going in one direction and then coming back. And then for flight 5, the duration was slightly the same. Altitude was much higher. We went to 10-meter height. And the distance was 129 meters and only one way. It was only one way because the helicopter was attempting to follow the rover. So we are trying not to be too far from the helicopter, from the rover, because once the rover is gone, now the rover is not paying attention to us at all. We need to follow the rover. The rover, if it loses us, they are going to continue with the mission. So we got one step closer to the rover to make sure that we're not going to lose link and lose capabilities to carry on with the testing of the helicopter. The helicopter is now doing taking images that are useful for the rover as well for the scientists. So you can look at different areas, take pictures, send them back. The one that you can see on the left is actually a picture that was taken during one of the flight of, during the flight 5 of the helicopter. Send back all these images to the rover so that the scientists can look and see if there is anything that they're interested in and something that they would want the helicopter to look closer to so that they could decide whether or not they want the rover to venture in this direction. And as you can see, the predicts and the actual measurement on Mars are arguing pretty well. So we were very happy with this result as well. Okay, now we're going to switch gear and we're going to talk about Mars Cube 1. Mars Cube 1 was the first interplanetary CubeSat. So this is the first CubeSat that ventured away from the lowest orbit. And so there was a lot of development that had to be done for this CubeSat to survive the flight, the trip to Mars. This CubeSat only did a flyby to Mars during the entry, descent, and landing of InSight, which is a lander. And during this phase of entry, descent, and landing, the CubeSat was flying by, was receiving all of the telemetry from InSight and was sending that in real time. The reason why we did that, it's because the orbiter could not do that. The orbiter would have recorded the data and would not be able, the orbiter doesn't have this ability to send data directly. It has to record and then send back. And so by the time it does that, it would not be in line of sight. It would be behind Mars, and we would have had to wait until the orbiter is again in line of sight to transmit all the data. And that would have resulted in many hours of wait. And so we didn't want to do that. So the former director of the lab of the Jet Propulsion Laboratory challenged JPL to find a way to do a real-time data transfer using a CubeSat, which called bent pipe communication, which means that as you're receiving the data at a given data rate, you need to transmit this data at the same data rate. So there is that's a feature that was very critical, very important, that we wanted to demonstrate using a CubeSat, and that's what we've done. And you can see here, this image actually shows you the concept. InSight, as it's landing, sends through UHF to these twin CubeSats, and then this CubeSat using X-band transmit the data back to Earth. So the key technology to enable that was actually this deployable reflectory antenna, where we have 3 panels that falls on top of the surface of the CubeSat, deploys using spring-loaded hinges, which is the easiest way you can deploy a structure, and the lowest risk approach as well to deploy such an antenna. It's initially held against the CubeSat using a burn wire. We apply a current to the burn wire, which burns this wire, hence the names of the burn wire. As soon as the wire opens up, the panels are being released because of the spring-loaded hinges. And then there is this feed that you see here that deploys once the reflectory are being deployed. So it's held against the surface of the CubeSat because of the solar panel. So once the the reflectory panel. Once the reflectory panel deploy, the feed can deploy. For those who are familiar with reflectory, you can tell by just looking at it that it's a very simple design. The elements are just patch elements. So if you design a reflectory like that with the tools that we have nowadays, for example, using TCRA grasp module to design a reflectory, it's not gonna take you more than a few minutes to design a reflectory like that. So there is nothing very difficult to design the reflectory. However, what you need to be very careful with when you design an antenna like that is the design of the feed. So the feed is very close to the bus of the CubeSat itself. So you need to make sure that there is no reflections on the bus of the CubeSat. So you need to taper feed in a way that the side lobe in the direction of the CubeSat are extremely low. And that's what we've done. I'm going to show you some of the details for that. And the other reason why the feed is the most important part of this reflectory, it's also because it's driving all of the performance. So the circular polarization is generated by the feed itself. The cross polarization is being driven by the feed itself. And the efficiency of the reflectory is being driven by the feed itself. So if you have a lossy feed, then that's going to be a big hit for the reflectory. There is ways to optimize the efficiency of a reflectory, but you have to play with the optical prescription of the reflectory. And on a CubeSat, we're not able to do that. So we're just doing what we can with the constraint that we have. We cannot increase the f over d, the focal length of the reflectory itself. And we cannot also play with the angles of where the feed is located. So those are trades you can play with. You could play with the distance between the feed and the reflectory to actually achieve a higher efficiency. But here we cannot do that because we are constrained by the volume of the CubeSat itself. So the feed was located as far as possible from the reflectory, but we couldn't go farther to achieve a better efficiency of the reflectory itself. That's why the feed is really the key to achieve the requirement of the reflectory. The reason why the reflectory was the obvious solution here is because we were not given any storage volume inside of the CubeSat itself. So that was the only options that we could explore. So the optical prescription that I was discussing about is actually shown here. So you can see where the feed is located, and we basically the pointing direction is was given by the feed prescription. We didn't try to change the pointing direction by changing the design of the reflector itself, because obviously you can get any direction, pointing direction that you want by designing the reflector itself. If you all to do that, but here the 22.7 degree was actually convenient for the mission itself, where the the UHF antenna needs to receive the signal, and at the same time, the reflectory needs to point toward Earth. So that worked out really, really well. So that's the reason why we stick with this design here. You can see the gain, the predict was much higher than what we need. We initially needed about 28 dBi. We ended up having 29 dBi, and it's mainly because the feed design was actually a very, very, very low loss. And I guess initially people didn't think that we can get a feed that was roughly 0.2 dB of loss only. We managed to do that. So 0.6 dB of loss, sorry. We managed to do that, and that's why we ended up with such a high gain compared to the requirement. And you can see that the predicts and calculation are actually in fairly good agreement. The cross-pole is not overlapping perfectly, and that's basically the feed itself. Cross-pole was not perfectly overlapping, but it's meeting the requirements, so it's not an issue at all. So for the feed design, this is what I was discussing about. So you can see the tailor that we used, 0.5, 0.8, 0.8, and 0.5. And we also use the trick on, so you can see the direction of where we actually feed the patch element. That introduce some asymmetry in the pattern of the feed itself. So you can see that in one direction, the side lobe level are much lower than the other direction. Guess what? This is where the bus of the Cubesat is. And as a result, the Cubesat bus is completely transparent to the feed. If you were to design a feed without accounting for tapering of the side lobe level, you would have a very big surprise as soon as you put everything together, the feed and the reflectory. Your gain would be a disaster, and the pointing of the antenna will be much more different. So those are the things that an engineer needs to think of when you're developing a technology, because otherwise you move forward and then you build everything, and then you realize you have a problem and you wasted a year of work. Obviously, when you work on such a fast track development like a Cubesat like that, you cannot afford any delay. So you have to be very careful and think about this kind of things ahead of time. And so then I'm going to talk about the UHF antenna, which was designed by my colleague, Dr. Emmanuel de Crosas. He published a few papers, and also in my book on a Cubesat antenna design, there is a lot of details there on how we actually designed this UHF antenna. It's actually a very neat design, and I always like to describe this design because it really shows on how a very simple understanding of the basics of electromagnetic allows you to come up with a neat design like that. So to get circular polarization, what do you need? You need two linear polarization. These two linear polarization needs to be orthogonal, and you need to excite them with the same amplitude, and you also need to excite them with 90-degree phase difference. So once you have all of these recipients, you will get a very, very good circular polarization. So what Manu proposed at the time was to use a loop antenna, excite the loop antenna in two different points, right? So if you excite on the bottom left of the loop antenna, you get linear polarization that goes in the direction that you see here, right? And then if you excite the same loop antenna on the other opposite side, on the right side, bottom right side, then you get another linear polarization, which is a 90-degree, which is orthogonal of the first one. So you have the orthogonal linear polarization, and you have the two linear polarization, which is very important. And the second thing you need to do is to find a way to excite them with the same amplitude, and you need to find a way to provide this 90-degree out of phase. And so as you can see, if you excite this first port with 0 degree and minus 90 degree for the second port, then you get a right-hand circular polarization. If you needed left-hand circular polarization, which we didn't in our case, then you just need to change the phase difference between the two. And so that's where it's very interesting. The second thing that about the design is that we actually use the Cubesat bus as a reflective surface. And there is no other way that you can avoid that, because at UHF, the bus, the Cubesat bus is so small that you have to work to live with it. And in this case, we live with it and you took advantage of it. And we also, it's not shown here, but you can see on the right picture that solar panels were also used as a reflective surface to even increase the gain of the antenna. So as soon as you put the UHF loop antenna on top of the CubeSat, then you increase the gain on the direction, opposite direction of the CubeSat bus. And then to feed the two port, we actually use this balloon. Oh, there is a mistake. I keep forgetting updating that. It's 0 degree and 90 degree here. And basically how we did that is we used the loop antenna as a ground plane. The loop antenna itself is the ground plane for the power divider and for the balloon. And that's what you see here. We actually use the loop antenna as a ground plane to allow us to actually feed the loop antenna points, this one and that one. I don't know if that's clear, but basically here we have a power splitter, and then we have a phase difference, which is just basically one from that point to that point. We have a much longer distance to have this 90 degree phase difference. And yeah, that's the neat thing about this. And then the design is very simple. We actually used springs to actually deploy this UHF antenna at the desired distance to get the gain increase that we want of 8.5 centimeter. And same thing, we will use the burn wire release mechanism to actually release this UHF antenna from the surface of the CubeSat itself. And you can see that we have a very tiny cable that feeds the UHF antenna. Okay, and this is the radiation pattern that we actually measured in the outdoor range of JPL. And you can see that's a very, very nice facility that we have, where we have this fixture which is transparent for RF. And on the bottom, to avoid having multipass, we actually have a bunch of absorber that improves the quality of the measurement. Otherwise, you will see some of the ripples. And yeah, so if you compare the calculated and measured, there is a very good agreement between the two. So we have the elevation plot on the left and the azimuth plot on the right. And those are measured results that were obtained during entry, descent, and landing of InSights. And that's the data that we received in the Deep Space Network antennas. And our telecom system engineer extracted all of the data. And so you can see the different phase of the landing here. Until we actually turn off after the UHF, after the lander actually lands. But you can see that there is one thing that you will not notice right away, is the fact that each of the CubeSat have a different receive power. It's about 2 dB of a difference. And the difference is actually explained by the fact that the DSN is used to communicate. The same DSN is used to communicate with the two CubeSat at the same time, but each of the CubeSat are in different direction. So you will have, if one of the CubeSat is on the peak of the DSN antenna, then the other one will be slightly off, and this misalignment is actually explaining the 2 dB difference between Marco A and Marco B. It was quite impressive because when we did a comparison of the antenna gain, we turned out within plus minus 0.4 dB, which is quite impressive when you realize that there is a lot of parameters besides the antenna that can influence these numbers, such as the SSPA output RF power, which is dependent on the temperature and things like that. So yeah, so that's that was very exciting to see that we were actually getting everything that we expected. Oh, and by the way, on the left is a picture that was taken by Marco of Mars, and you can see actually the reflectory panels on the top, and you can see the tiny feed on the bottom where you can see 4 patch elements. Okay, so then I'm gonna go a little bit faster on the other technology that we developed. This one is a deployable 1 meter deployable reflectory antenna, which is compatible with a 6U Cubesat, and that's the limit that we can achieve with a 6U Cubesat. Do something bigger than that, and we achieve more than 47 dBi with such an antenna. You can see the prototype that we fabricated, deployed to demonstrate the deployments, and then this is the measurement result that we obtained from this prototype. We achieved more than 47 dB of gain at 35.75 gigahertz. And then now I'm going to talk about mesh reflector. We've done a lot of work for small satellite and CubeSat. So the first one is Raincube. Raincube is the first radar in a CubeSat where we have this 0.5 meter mesh reflector where we were given one view of storage volume inside of the CubeSat, which is 10 by 10 by 15 centimeter. And we were asked to develop an antenna that achieves more than 40.5 dBi of gain with linear polarization at Ka band, 35.75 gigahertz, which is where the precipitation radar is operating. So this is the antenna that we designed, where we managed to fold the antenna on this small canister of 1.5 U. You can see in the center we have a waveguide, which we call telescoping waveguide. And then we have in yellow the feed horn, which is a multi-flare horn, which basically allows you to get similar performance than a corrugated horn. So with very, very low cross polarization and very, very low side lobe level. But the fabrication is much easier and also avoids you to have any problem during the deployment if there is a misalignment between the telescoping waveguide and the horn itself. You don't want thing to get stuck into the corrugation, so that's why this design was preferable. Then we have all of the ribs of the mesh reflector that folds around the feed horn. And all of that is very important because that drives the optic of the reflector antenna. And we had to do a lot of trades to mitigate the complexity of the mechanical deployment and still achieve the maximum RF performance we could get. So myself and the mechanical engineers, Dr. Jonathan Soder, worked very tightly together for several years to actually achieve this ideal RF and mechanical performance. And we were very lucky to be successful in flight with the deployment. So let's look at the deployment, the antenna on the ground in the lab. So here you can actually see that you have a 4 screws driving motorized system where it pushes out the antenna itself. And once we actually reach the, let's see, 1 second, I'll go back. So up to now, everything is very well controlled by the motor. And at this point, you can even drive the motor to actually fall back. But once you reach the release of the mid hinges of the ribs, which happens right now, that's the end of it. And then the final step is to deploy the sub reflector. And the sub reflector is being pushed out by a spring which is located right there around the feed horn. So all of that was done with several iterations to improve the mechanical robustness of the design. So it did not work right away. That's not magical. So we had to go through different iterations. Initially, we were using an inflatable deployment, and we realized that it was not ideal at all, and that's why we switched back to the 4 screws motorized system. And yes, so that's a very good design, mechanical and RF. I invite you to look at this publication, or you can also look at the book that I mentioned earlier, where we provide much more details. For the RF design, the few things that you need to know of. First, the cassette grain design was preferred because mechanically it actually helped a lot, because the sub reflector is located under the focal distance. So that allows us to reduce the number of deployment to deploy the feed and the sub reflector. So it reduces it to only one deployment. So that's a significant improvement from a mechanical point of view. And although it's not necessarily the best design for RF, this is what we decided to go, because as a trade, it makes more sense to advantage the mechanical robustness and take a small RF hit behind that. So then the second thing you need to be careful about is the fact that a Ka band, the parabolic reflector, is not a parabolic shape anymore. And that's because between the ribs, each ribs were limited in terms of ribs. So you have to decide how many ribs you want. And obviously the minimum size of rib would be 3, where you would have 3 triangles. That would be really bad. And then you can increase as much as you want. If you get to an infinite number of ribs, then you have a perfect parabola. You cannot get to the point where, from an RMS point of view, it will not have an impact for at Ka band. That's not possible, because if you do that, the number of ribs will be too much, and the chance of jamming during the deployment will be too high. So that's not something we want to do. So we limit it to 30 ribs, because from a mechanical point of view, it made sense. That's where the less risk will be. But also from an RF point of view, we managed to compensate for the surface aberration of 30 ribs by refocusing the focal point of the feed and the sub reflector. So by doing that, we refocused the radiation pattern, and we got some of the gain back that's caused by this surface aberration. So I think at the end we had only 0.3 dB of loss or something like that due to the surface aberration. So that's very minimal. We ended up having more than 56% of efficiency, and we also used 40 OPI, opening per inch mesh, because at Ka band it was required to mitigate the loss. So then this is a video of the deployment on orbit. So we couldn't see the entire thing, but we could see sufficiently enough to say, well, the mesh reflector seems to be to have deployed properly. The sub reflector deployed properly as well, and the feed, which you see in the bottom, also deployed in the right location. How do we do that? So before launch, we actually take the same picture in the lab, and then we overlap the two. And once we overlap the two, we can tell if something is wrong. And we did that very quickly, and we didn't have any problem. So you can see here we actually have the mid hinges that you can see very well in this picture. And we also have a cable that ties all of the ribs together. The reason why we have this cable is that we don't want a big delay between one side of the deployment of the reflector to the other. So by tying up every single ribs together, we ensure that they follow each other, so that the mesh in areas. And I just wanted to show some of the I realized that we just published a paper focused essentially on the science. So I should have put the paper here, but feel free to look on IEEE or reach out to me if you're interested in the science. The paper is very detailed and very, very well written. So here is an example of the typhoon where I put the picture of it on the left. And you can see there is two data. There is two data here that overlap. Is provided by Raincube, which is the vertical line that you see there. And the one on the bottom is taken by another Cubesat, which is a radiometer, which is a passive instrument. And the scientists wanted to see what kind of accuracy we could get by having two passes that are close to each other. In this case, they had a pass of within five minutes. And the scientists were actually extremely impressed by the accuracy that they got between the two Cubesat, which gave us a lot of ideas for future mission. And I'm going to talk about that now. Yeah, so after that, the scientists asked us to come up with larger antennas, as usual. So we started with 0.5 meter, then they asked for 1 meter. And we actually worked with this small company, Tendeg. We actually worked with them to develop this mesh reflector, 1 meter mesh reflector, that could potentially extend it to even larger reflector. And so you can see the deployment on the bottom. And this specific design would love for a 12U CubeSat, and it takes 1/4 of the 12U CubeSat, which you can see right there. So it has a boom that deploys the reflector away from the CubeSat, and then the reflector deploys. So now let me show you. So this one specifically turned into, we started with a radar antenna. It was then turned into a telecom antenna, which is very simple. As soon as the reflector is designed, you have to change the feed. We developed two feeds, the feed at K-band and one at X-band. We purposely designed two different feeds because some mission will want to use X-band only, and some others will want to use K-band only. And they can be co-located if they wanted to use both of them at the same time. And we achieved very, very good efficiency. At X-band, we got more than 62% with more than 36 dBi. At X-band and K-band, we got more than 60% of efficiency. And at K-band, we got 48 dBi with circular polarization for both frequency, obviously. So this is the design that we used at X-band. This is the design we use at K-band, which is just a multi-flare horn combined with a polarizer. The polarizer provide right or left circular polarization. Most of the time, we just put how do you call that? We don't even put a load on the port that we don't use. We just cover these ports because it doesn't really affect too much the performance of the polarizer. Yeah, so. And you can see actually the design, and that's actually the model that we used on GRASP that I show on the bottom. You have the reflector, the CubeSat bus, and the boom that are represented with MLF. And the reflector itself was just using PO, physical. And the feed is here represented with a spherical wave expansion and exciting the reflector. So two things, we actually account for the reflection from the feed to the CubeSat bus and boom to the reflector, and the feed to the reflector, which is the main contribution. And we ensure that the reflection on the bus is not impacting the performance of the antenna itself. So that can be done by designing the feed in a way that the side lobe level are small enough in the direction of the CubeSat bus. This is the performance at X-band, and I'm not going to go into details, but we got very good accuracy being calculated and measurement. And this is the, let me see. Oh, I'm sorry, I have a typo here. It's a K-band. So this is the performance at K-band. I need to correct that here. And as you can see, K-band. Okay, one thing I have to say here. I always want to be very, very clear about that, because as you can see, the accuracy is overwhelmingly good. But the reason why it's overwhelmingly good, it's because we actually do a measurement of the surface of the reflector. So we deploy the reflector, and then we measure with a laser the surface of the reflector itself. Then we feed our grasp model with the surface, and then we plot the predicted with measurement comparison. And that's the reason why you have such a good accuracy. The other thing that we did, and we need to be careful with, is that you do sufficiently enough deployment to verify that every time you actually get the same surface. If you get the same surface, more or less, right, if it's small variation, it's not a big deal. But if you get the same surface every single deployment, then it is okay to do that. And in most cases, all we want is to have a good prediction of the radiation pattern. For telecom, this is important, but for radar, it's even more important. So for radar, they really want, the knowledge is very important of the performance of the antenna. So we need to ensure that every time we deploy, we get the same results. Okay, so then I showed you an example earlier of the science that we got combining radiometer and the active radar, the Raincube radar. And that gave us an idea to our scientists, and they are looking at different small satellites that will be used both of the Raincube instrument combined with the radiometer instrument. And that's an example of this, where you can see the Raincube antenna is actually, I mean, the active radar antenna is going to be this one, which is very large. It's more, this one's 2.1 meter. And then we have the radiometer, which is located on the back right there. And so they can combine both, and they can compare the result. They can, the scientists can use both of these. So that's very attractive for the scientist community. So here, what they wanted was to have these 5 beam, and by taking advantage of the spacecraft motion, you can actually have a 3 dB overlap, which is what I plot on the right. Which basically, as the spacecraft move, you will get this beam that will cover all of that, right? All of these. You have this beam that will cover all of these. This beam will cover all of these. So at the end, you have a 3 dB overlap between the 5 beam. And that's a trick that they use to cover the map of Earth much faster. Then the second concept that they were looking at wanted to use 2 reflectors. One was using a deployable mesh reflector, which is an offset mesh reflector, and one which used the Casa offset reflector. Same thing, they want to use the motion of the spacecraft to actually get 1.5 dB beam width overlap, which is what you see here. If you have this one, this one, this one, this one, this one, this one, they all provide 1.5 dB overlap if you take into account the motion of the spacecraft. The trick here is that they wanted the 2 antennas to overlap. They want these 2 antennas, the offset mesh reflector and the Casa antenna, to have the exact same beam. And that's what you see here. The solid mesh the solid lines are the solid reflector, the Casa antenna, and the dashed line are the deployable mesh reflector, offset mesh reflector. And as you can see, we could optimize the location of each of the feed to be able to do that. So that's a very, very neat trick that we haven't published yet. We did the design using TCRA grasp again, and I'll probably publish something in the near future on that. But yeah, that's a very neat optimization method that we use here to actually manage to do that. How much time do I have?
It's up to you, Nasir. Sorry.
Okay. Okay, I just want to make sure I have I can take questions, so I don't want to.
Sure.
So I don't know if you want. Do you want me to take all the questions at the end, or?
Exactly. We will have a Q&A session afterwards.
Okay. Okay, so I'm gonna try to go a little bit faster now and finish within 10 minutes so we have time to take questions. So it's more useful to people. I don't want to be the only one talking, so I'm gonna show you the rest just to give you an idea of what we do and then we can go to the questions. So now we'll talk about metasurface antennas. For the work on metasurface antennas, I've been working with Dr. David Gonzalez from University of Rennes. He's a CNRS researcher. He's probably one of the best in the world in metasurface antennas. So him and I have been working very closely in developing different type of metasurface antennas that we could use for flight missions. The first one that we've been looking at with other colleagues was this one, which is completely made of metal, entirely made of metal, where you can generate either linear polarization or circular polarization by modulating the surface wave with these elements, which are elliptical conical elements. And so basically you're changing the rotation of these elements to change the impedance across the surface wave, across the metasurface. So different things need to do. First, obviously, we had to develop the design methodology for that. So I invite you to look at the paper that David wrote, which is extremely detailed and very, 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 very good paper. So I invite you to look at it. And then there is the other aspect, which is also the fabrication methodology. And we first started with a 10 centimeter antenna, and most recently we fabricated 20 centimeter antenna. And I think that now we can go by doing a single block, right? We can go up to 30 centimeter with the latest advancements of this additive manufacturing machines. So we achieved a very good efficiency. I think I have another plot. Here we go. So this one is the performance shown for the 20 centimeter antenna, where we achieve more than 50% efficiency in the center frequency, which is quite impressive. And you can see that the predict between calculated and measured in each of the cross of the antenna are actually pretty good. Cross pole is matching very well, co-pole is matching pretty well, and the gain is fairly good as well. So we were very happy with that. And now, because we achieve 50% efficiency, we are in the realm where this antenna can actually be extremely attractive for space application, where we need to fit a flat antenna on small satellites. So that's or even lander and rover. So that's getting very exciting. The next step to really make this antenna competitive against reflectory or other type of antennas is to actually no, against reflectory it's already competitive, because most of the reflectory that we use for telecom, they are single frequency. We can do single frequency with those, and we can actually achieve higher efficiency with this antenna now. However, to be competitive with other type of antennas, such as reflectors, parabolic reflectors, or multi-band patch array antennas, we need to come up with designs that cover two frequency or more, and that's what we're looking at right now. We're trying to do a multi-frequency with metasurface. Here is a picture of a video of the fabrication. So you can see the way they actually fabricated this metasurface antenna was by doing different section of it. So you can see that the one they are building is this one, and so you can see it's real time. The fabrication is real time, so that's extremely fast. So we can build this antenna in few minutes. So for the for all of these new flight missions that are requiring to send these gigantic constellations for internet, for example, we have SpaceX and we have Amazon who are working that very, very actively. Those are the game-changing technologies that could revolutionize this sector, this sector, because the cost of fabricating hundreds of thousands of these antennas would be extremely cheap because of this manufacturing technique. So then we also developed this other metasurface antenna, which is a combination of to excite the metasurface, and on the top level, it's two layers. The bottom layer is the pillbox that excites the top layer with coupling slots, and then the top layer is getting this I forgot the word. Sorry. We maybe I have a plot after no. So we have two feeds on the bottom layer that excite the top level, the top layer. Each of the feeds excites the metasurface antenna, so that we have two beams with a 3 dB beam with overlap. And so this is only possible to do that with this type of antenna. And the reason why, it's because we can only get a very good isolation between the two ports with this type of antenna. So that's the reason why we were looking into that, because the radar that I'm showing the schematics, high-level schematic of here, requires one port for transmit and one port for receive. So you have only the entire radar is a system on chip, and the only thing that you have outside of the system on chip radar itself is the power amplifier, obviously, and the antenna itself. So we excite the two one port for transmit, and then we connect to the receiver ports onto the other port. So this is important that the two beams are overlapping so that they can actually get the data from transmit and receive on the ground. They're actually using the overlapping area to do that. The other way to do that is by using two different antennas. But obviously, it's much more bulkier to do that, and that's not the ideal thing to do. So by doing that, we actually reduce the mass quite significantly. You can actually see the antenna fabricated here. The radar is actually located behind. It's actually even smaller than the antenna itself. That's why the system on chip is becoming very attractive. And due to the fabrication process of this antenna, which is basically made of metal sheets fastened together, we have a very good accuracy between fabrication and calculation. And then I'm going to finish with the Europa Lender. The Europa Lender is a mission concept. This mission concept was initially planning to send an orbiter and a lander. The lander will transmit data to the orbiter, and the orbiter will send all of the science to Earth. However, the mission cost was way too expensive. So they came back to us and they told us, hey, if you really want this mission to happen, you will have to find a way to reduce the cost. To reduce the cost, the only way to do that was to remove the orbiter itself. And the only way to do that was to enable direct-to-Earth communication from the surface of the lander. And that's what everyone thought was impossible to do, because to do that, we needed an antenna that had an efficiency of more than 80%. And all the antenna we have flown to date for any NASA missions were much lower than that. And when I say 80% efficiency, I'm not talking about power in, power out. I'm talking about area that you use. So you calculate the maximum directivity that you can get based on the area that you have of the antenna, and you compare that with the actual measured gain, which includes the loss of the antenna itself. Yeah, so that's very, very important, because that's much more difficult to have an antenna that use efficiently all of the area that it has, all of the aperture that it has. So that's why I want to be very clear on what we define as an efficiency. So this antenna, actually, the one that we proposed, 100% of efficiency power in, power out. No, sorry, I'm incorrect. Using the directivity obtained is the same directivity that we obtain when you use the area, the total area that we're using for the antenna, which is not easy to do to start with. So when you use, for example, when you use a reflector antenna, parabolic reflector antenna, you will spillover and taper loss. And as a result, you will start at 80% efficiency. With this antenna, we managed to excite every single element to have the same amplitude, got no spillover and no taper loss. So we started at 100% efficiency. Then everything else is dielectric losses or ohmic losses coming out of the antenna. And we had to ensure that this will remain within 80% efficiency. Everyone thought that it was impossible because we've never done that. And it was even harder because on Europa, we have very stringent requirement. It needs to survive the cryogenic temperature of Europa, and it also needs to survive the high radiation level of Europa, which is even harder because the antenna is located outside. You're not allowed to have any dielectric because otherwise it would constantly have electrostatic discharge. So you would basically have arcs happening inside of the antenna that could propagate to the telecom subsystem and destroy some of the active components. So that's where you need to be extremely careful when you design that. So we design, and then on top of that, the antenna needs to be dual frequency with circular polarization. And that's another aspect that was very challenging. So this is the antenna concept that I proposed, which when I originally proposed that, I was laughed out because nobody thought that it was actually possible to achieve this performance. But I was given the opportunity to demonstrate that it was feasible. And so we went into different steps. First, we fabricated a subarray of 8x8 patch elements. Then we did this 16x16 patch array, which is basically 2x2 subarrays. And each of these subarrays are connected with waveguide. And that's how we actually managed to keep the efficiency extremely high. And then the main efficiency, the main innovation here is actually this single element where you excite with a single port, with a single point, and you still get two frequencies and circular polarization, which is not an easy feat to achieve, and all in metal. So you can see here the antenna, that was the subarray that we actually initially fabricated and checked that the performance were as expected. As you can see, the accuracy between calculation and measurement is quite outstanding. And the aperture efficiency is more than 80% at both uplink and downlink. So to give you a comparison with other antennas that have been flown before, so the original baseline that we used on the Europa Lender before I jumped into the project was this radial slot array, which does the good for a single polarization, but extremely bad when you're trying to get two polarization because they are resonant elements. As you can see, the efficiency, 34% efficiency at uplink and only 18% efficiency at downlink. And that's where I came in and I said, no, I think I can do 80% efficient. Then MSL and MER, which are don't have the we have, basically no dielectric allowed, they did not even achieve more than 50% efficiency. And our design, which is about the same gain, right? We're comparing apple to apple, they're about the same gain. We actually achieved more than 80% efficiency at uplink and downlink. So we achieved what we claimed was possible. And as you can see, the mass is also significantly lower. And the beam width is much better than the radial slot array because the efficiency is much better. If your efficiency is better, then you're using the array much better, so your beam is going to be much broader. So you want to get can keep increasing the size of your antenna if you have a poor efficiency, but then your beam becomes much narrower and narrower and narrower. And the pointing requirement for the gimbal is much more drastic. So all of that is traits that you need to keep in mind. Then this is the 16 by 16 antenna where you can see the waveguide feed array in the back that feeds every single subarrays. This is the S11 measured and calculated, which agrees really well. And then the calculated and measured for the radiation pattern as well, which agrees very, very, very well as well. And we achieve very, very good efficiency at uplink and downlink as well. And then this is some artist rendering of the rover is folding and after it deploys with its gimbal. And this is the final antenna. So that was to give you an idea of scale. And this is the actual antenna, 32 by 32. And we finally achieve what we call technology readiness level 6, which consists of qualifying the antenna for flight. So we can now fly this antenna whenever needed. So, and this is a pretty neat picture of the antenna itself on a mock-up that's used for the landing gear demonstration. And those are the legs that here that allows the lander to land on any surface, whether it's flat or not flat, it will land on it without any problem. And to finish the talk, here's a list of papers that I invite you to look at. There might be others. Yeah, I invite you to look at the one on the Raincube if you're interested in the science. I did not include it here. I will have to add it. Feel free to ask me if you're interested. And I also invite you to take a look at the book that we just published at the beginning of this year. It's been a lot of work to actually put that together. It summarizes a lot of the antenna technologies that we developed for Cubesat, and it really goes into the insight of all the traits, all of the requirements, and how that impacts the design and things like that. So if you aim to be an engineer, so that I think that's a good book to look at. So now I'll take any questions that you might have. Thank you.
All right, thank you very much, Dr. Nasir, for very nice, informative presentation, for your amazing work. I mean, for all this space science mission, it's a very interesting, and it's like a first time for me to look at all these kind of antennas. We have actually compiled questions that has been asked in the that chat box. Please allow us to share those, Hafiz. Mr. Hafiz. We have 8 questions actually. Okay. All right. The first one, Nasir, from Ali Al-Karagul. The Rover antenna seems to be much thicker than the helicopter antenna. Is this entirely for mechanical robustness? Does it affect antenna bandwidth?
Yes, that's a very good question. So obviously, the thicker the monopole will be and the larger the bandwidth will be. So that's a very good observation. However, on the helicopter, we were not able to actually have a bigger than, I think was even less than a millimeter of a wire because it's on the solar panel and we cannot have any shadowing on the solar panel. So that's the reason why we didn't have something thicker for the helicopter antenna. However, on the rover, we didn't have any mass constraints or shadowing constraints. So as a result, we made it thick enough so that it's robust and it covers the entire bandwidth in case we have any movement due to thermal changes. So that's the reason why. If we're given the ability to be more robust mechanically, we're doing it. And if we're given the ability to get more bandwidth, we'll do it so that we're more robust to thermal changes. For the helicopter, that's what explains the difference between the two.
All right, thanks. Probably next question from Mayuri Rao. How are antennas designed for operation in space tested pre-flight on the ground? Given the environment in which they are tested will affect measured properties like gain, S11, and etc. Yeah.
So it's a okay. Give me 1 second. Yeah, so I mean, it obviously depends on the mission. Every mission will have different environments, so the qualification will be different for each of them. For example, when we go to Mars, okay, let me start with what's in common. Vibration testing, shock testing, even though the levels are going to change, obviously. We usually always do S11 measurement, radiation pattern measurements, and then depending on where we go, we might do high power testing as well. So if we're in vacuum, we do multipaction when it's required. And when we're on Mars, it's partial pressure, so we do high power testing for ionization breakdown as well. So those are added tests that are associated to flight specifically. And then the vibration shock, those are tests that are related to the launch levels or deployment in space. Shock can be caused by pyro being fired in space or the landing on Mars as well. So those are things that and then there is a thermal cycling as well, where you verify that the S11 does not change or when you're cycling over thermally, so you're going to very cold or very hot. You want to make sure that there is no joints that breaks or things like that. Let me think. For Europa Lender, it's we have very high radiation levels, so we also do Isd testing, where we put the antenna in a chamber that is in a vacuum, and it's in cryogenic temperature, so very cold, less than minus 170 Celsius, and we bombard the antenna with electrons. And what we do is that we connect the port of the antenna and we look at how much discharges are being detected at the port of the antenna, because it's going to propagate to the telecom subsystem and might deteriorate other hardware. That was that big challenge for the Europa Lender antenna as well, which we managed to take care of by designing the antenna very well. And I think that covers the question.
Yeah. I think it's perfect. All right. Third question is the from Ashmat Mardiansha. Is there any license frequency in Mars?
No, that's a great thing about being the only one working on Mars. However, now we are no longer the only ones. We have more people going to Mars, but for a very long time we were the only one. And obviously there is no rules. However, as we are more people sending rovers and potentially sending astronauts, we'll have to discuss that, and we'll have to work together. Nations will have to work together to ensure that we're not interfering with each other. Right now, all of the rovers that are on Mars, they are very far away from each other. Even the NASA's rover and lander are very far away from each other. So that's not really a concern. So that answers the question.
All right, thanks. That's good. Yeah, the fourth one is, what frequency do you use for communication in Mars and also between Mars and Earth? And why use that band?
Oh yeah. So that's a very good question. So traditionally, we've been using for deep space communication, not just Mars. We started with S-band, then we moved away from S-band and we focused on X-band, and later on started working with Ka-band. So most of the deep space mission carries X-band and X-band and Ka-band, and the reason why they always carry both is that Ka-band is great, allows you to achieve very high data rate. However, if you're on a very rainy days or cloudy day, the Ka-band link might be affected. So we can switch back to X-band if necessary. So that really depends on, and also depending on the pointing of the antenna, the pointing capabilities, the pointing knowledge of the spacecraft, you might want to switch to X-band with low gain antennas with broader beam. So those are traits that we account for. So that's the reason why we usually carry both X-band and K-band. However, for moon missions where JPL is much less used to work on, we still carry S-band because the links are very, very short range. So we can still work with S-band and get decent data rates. So the reason why we use X-band and K-band is for convenience, because of the technology that are available. So the SSPA, the power amplifier that we have, or the Twitter that provides sufficient power to operate at X-band or at K-band. So that's also other reasons why we use these frequencies.
Okay, that's good. Thanks. Yeah, next one. How can we improve the overall efficiency of refractory antenna?
So there is I forgot the name, but there is a very good book on reflectories that I invite you guys to look at, where there is a chapter dedicated on that, where they explain how important the optical prescription of the reflectory is important to actually get a good efficiency. So obviously you will get ohmic and dielectric losses from the reflectory, but they're very minor. It's not significant. So most of it is related to spillover and taper loss. And that's where you're losing a lot of efficiency. But by playing with the optical prescription of the reflectory, you can actually improve the efficiency of a reflectory. So if you have the flexibility to put your feed as far as possible, you really have this trait where you can play with the F over D of the optical prescription to achieve the highest efficiency.
Okay, good.
And
Thanks.
obviously, what I mentioned is also the feed. You got to be very careful with how you design your feed, because if you have 2 dB or 3 dB of loss in your feed, then that's game over. So you need it.
Okay, question number 6, multi-beam antenna mutual coupling effect, and which shape is preferable for use, like hexagonal or any other shapes from the same Sogata strategy?
I think Sugata, sorry, is mentioning the positioning of the feed. I think that's what he's probably mentioning. So the positioning of the feed is actually not we didn't decide that based on the coupling effect. We decided that based on the overlap that we want between the elements. However, the trick here is that the absolute overlap between each of the feed is very, very large. It's more than 15 dB. Because what we do is that we achieve this 3 dB overlap or 1.5 dB overlap by accounting for the motion of the spacecraft. So in actuality, the beam themselves don't have this 3 dB or 1.5 dB overlap. It's only on the footprint on the ground that by moving with the spacecraft, you're covering everything so that they overlap after. It's always very tricky for me to explain that, but I think you need to visualize it by draw on a piece of paper the circle, and imagine that the spacecraft is moving, and you will see that all of them, you will have the footprint that will follow each other, and then as you go around the globe, they will all overlap each other within 3 dB or 1.5 dB, depending on the design.
Okay, thanks. Question number 7. I think Mr. Hafiz is trying to project it.
Yeah.
But anyway, if I can say it here, what are the prospects and challenges of 3D printed metasurface antennas as SAR sensors on board small satellites in LEO, in LEO orbits, I think. Yeah. Can you get my question?
I'm not sure I understood the question.
Now, what are the prospects and challenges of 3D printed metasurface antennas
Yeah, so the fabrication itself, the limitation is the surface roughness. So basically the small features of the element themselves and the size of the antenna itself. So as we want to build an antenna that's larger, we need to be smarter about it because we'll fabricate them in pieces. Then, in terms of surface roughness, unless these 3D printing machines gets better, we will not be able to go above Ka band. And right now, Ka band is the limitation to fabricate within the expectation. Above that, it's starting to be very, very tricky. We are very interested in using these antennas at W band. So we're hoping to improve the fabrication methodology. Obviously, we personally don't fabricate the machine, so we can only wait for the commercial world to improve that. But what we can do is work on processing, chemical processing to improve the surface roughness if necessary. So those are things that we're looking at to see if that's possible.
Okay, cool, nice. Another question from Christine Shabazian. I would like to know the level of complexity of designing your meta-surface antenna and what kind of software you use.
Yeah, so meta-surface antennas, it's really still some of the few antennas that really requires a very good theoretical understanding. So again, I invite you to look at David's paper where you can see the insight on the theoretical design of it. Once you understand the theory behind it, what you do is that you actually design, you create a database for each of the elements where you have to map these elements to elements. And then you reconstruct with a MATLAB code or any other code that you have what element needs to be where. Then you put that into your tools such as HFSS or CST or anything tool like that, and you do at the end a full wave design for that. But it really starts with a good understanding of the theory. Then we use the full wave tools to generate the database, and then for the full wave simulation at the end when the antenna is ready.
Right, good recommendation. Yeah, question number 9. Is the main reflector of the Casa antenna made up of metal or any other RF reflecting material? This intrigued me because you have the reflector folded.
Yeah. So absolutely, actually, that's a good point. This is just a metal reflector. So it's there is nothing really innovative there, and we didn't have any problem because it could actually fold on top of the feed because the aperture of the feeder horn was large enough to just sit on it. So that was not an issue. However, at some point we were, in case that became an issue and we couldn't fold everything, we were looking at using a reflectory for that. But you would have an impact in terms of efficiency if we did that. So we didn't do that because we didn't have to, but that would have been something interesting to look at. Definitely possible and not too difficult to implement.
Okay, all right, good, thanks. Yeah, I think we have another 1 or 2 more questions, Nasir.
Yep.
Yeah. Yes, number 10, why efficiency of array antenna is less? How to improve in 32 times 32 of array antenna?
Yeah. Good point. Yeah. I think it was around 73% instead of 80. It's because of a fabrication issue that we had, and we had a mistake was made when we were assembling the antenna that we had to cut afterwards. So we had to reopen and reconstruct, which was not great because it was not meant to do that. And as a result, the efficiency went down after we did that. But overall, we've demonstrated that we can fabricate the large array to meet the 80% efficiency without any issue. So we are not very concerned about that. And also the other thing is the requirement at uplink is much less stringent than downlink. So what really matters is the efficiency at downlink, which we had 80% efficiency. At downlink, we have much more power coming from Earth, and we have this very large antenna. When we are doing downlink, we have onboard power, which is only limited to 100 watts, and our antenna size. But uplink, we have more than 20,000 watts on the DSN antenna. So that's why it's not too much of a concern, even if it was slightly lower than 80%. But bottom line, don't make mistake when you are assembling such a large antenna, because it's not that easy to recover.
Okay, maybe last question before we open for live session or live question afterwards, if you have some time. How do you take into account of impact of thermal deformation in space on antenna radiation pattern, where you do antenna design and ground measurement?
Yeah, that's a good question. That's a good question. It's not that easy to answer because it really depends on the antenna. So I'll give you different example. Let's say a horn antenna that's entirely made of metal. So let's say you use aluminum, which what we use most of the time. You know what the CT of the antenna is. I think aluminum is 26 ppm part per million. So you can do the calculation very easy. So let's say if you know that your antenna will be between -100 to +100, you can do the calculation to know what the expansion will be at hot and what the contraction will be at cold. So you just apply a scaling factor to predict with your simulation what will be the impacts. And then obviously what you need to do as well is you know that your S11 is going to shift on the right or on the left depending on the temperature. So you need to make sure that you have what we call thermal guard. So you have a bandwidth that's large enough so that you're not being impacted by this change of temperature. Then for the Europa Lender antenna, for example, because it will be operating at cryogenic temperature all the time, we decided that simulation was not good enough. So we decided that it was important to verify the S11 at cold and hot, but also the radiation pattern and the gain. And turns out that we found out after doing the measurement, I should have shown that it's actually super exciting how we did the measurement at cryogenic temperature in a near-field chamber. But what we do is put this antenna, this gigantic antenna, into a foam. It's a closed box that we fill with liquid nitrogen to get to this cold temperature. We have a bunch of thermal controller, what we call TC, in different locations to verify in real time what the temperature are. And at every temperature we're interested in, as we're going down in temperature, we stay there and we check the radiation pattern. Then as soon as we verify the data, we go down in temperature, we check again the radiation pattern. Everything was as predicted. The S11 was shifting the way we expected it, and the gain was impacted by the S11. So at the end of the day, verifying the S11 is really the right approach to take. So that's the bottom line. But sometimes when it's that critical, it's mission critical, it is better to do the direct test campaign like that. So that's why for the Europa Lender, we decided to do the measurement at cryogenic temperature. Antennas that are made of dielectric, that are more complex, then it becomes more tricky, and that's where testing is very important. If it's all made of metal, you can get away with it by saying by simulation we prove it's good. But when it's much more complex, you have dielectric, you have features that you don't know whether mechanically they will survive or not. It's important to do a thermal cycling and check at least the S11. Okay.
All right, good, thanks. Yeah, question number 12. How to find E-plane and H-plane orientation of E-field in antennas?
Oh, that just depends on the antenna. It really depends on the antenna and the type of antenna they're using. So it's difficult. So for example, if you have a patch antenna, right, You feed in the bottom, you know that the polarization will be vertical like this, right? And so the E plane will be in this direction and the H plane will be a 90 degree from that one. So it really depends on the antenna. So what I advise here is try to read as much as possible books on antennas where they explain the basics of antennas. So you understand how every antenna is behaved, and then it will be instinctive for you. For any antennas, you'll know what the E field and E plane and H plane will be. Yeah, it becomes an instinct quickly. But you need to accumulate this experience to be able to, just by looking at any antenna, know how the field will be and where the current will flow and these things like that.
Okay, thanks. Next one. Yeah. What are the current trends for Cubesat antenna at UHF bands? Our planar structure.
So that's a good question. Okay. Yeah. So I'll give you the example of a Marco. So Marco, the first thing that was proposed was to use a patch antenna, which in my opinion was a very bad idea. Because what happens is that if you use a patch antenna to fit within the volume that you have at this frequency, which is roughly 420, I think, megahertz, what happens is that the patch is going to be gigantic. And to make it fit within the size of the CubeSat, you need to use very, very high dielectric. So you are going to look at maybe 20, maybe 40 epsilon r or something like that. So at the end of the day, your bandwidth is going to be very narrow and your efficiency is going to be really bad. So that's why it was not what we decided to use for Marco. And the loop antenna was much more attractive. So, but again, it's a trade of complexity, because obviously the loop, you have a deployment that you have to handle. So if you can live with a, might be something you want to explore. It's really a trade off for your mission, always specific to your mission.
All right, thanks. Yeah, we have 3 more questions, Dr. Nasir, before we close this session. Okay. I will stop receiving the question. Actually, you have been talking for 2 hours already. So anyway, the 14th one is the what material was used as mesh in Raincube? What electrical properties were taken into account for deciding upon the material, like relative permittivity?
Yeah, so the material, I'm sorry, but I always forget the name of this material, so I won't be able to tell you. Yeah, I forgot what it is, but look into my paper. It's written very clearly. And let's see, electrical. Yeah. No. So the material that we use is gold plated. So you assume that it is a reflective. I mean, a conductor. It's not. You don't need to account for any permittivity in there. It's just conductivity. So once you account for the conductivity, actually even the conductivity is not that important. What's really important is the opening per inch. So if you look at the paper I wrote on Raincube, you'll see that the opening per inch is very important because it tells you how much losses you get out of it. So we did a lot of work to actually predict that properly. And then after the fact, we did measurements on different type of mesh to actually see the difference from one mesh to another. We actually found some mesh that are 30 opening per inch, which are easy to work with. That work pretty well at K-band as well. So that's something that we used for the large 10-leg antenna as a result. So for the name of the material, I invite you to take a look at it because I forgot what the name is. But yeah, thank you.
Okay, second last question. Can you explain about space-borne synthetic aperture radar and what type of antenna should be used for SAR purpose?
For synthetic aperture radar, the type of antenna that needs to use, well, they need large antennas to start with. So most of them, they use either deployable patch array. So actually, there's 2 main companies that are working on synthetic aperture radar for commercial. There is Isd in Europe from Finland. These guys are using patch array antenna. and it's a fixed beam. There is no beam steering. I believe there is no beam steering in their antenna. And then there is another company located in the US, which is I forgot their name now, Capella Space. And these guys are using the 10-day antenna, actually, based on the pictures they posted, I can only assume, which is the one that I was showing, which is the deployable mesh reflector. And so, yes, so that's the type of antenna used for synthetic aperture radar. I'm personally not an expert on synthetic aperture radar because I never worked on a mission that does it. So I'm not the best person to talk about it, but those are the type of antenna that I know they are currently using. Yeah, the one thing that is important for synthetic aperture radar though is so if this is your spacecraft, the beam, you need to have an angle of incidence. That's very important for synthetic aperture radar. So that's one of the features that they have to take into account when they design them. That's why using a offset mesh reflector is much easier to do that, much easier than Aperture array. So yeah. And I say that ICE was using a fixed beam. I'm actually not sure, so you might want to double check that. Maybe they have some steering capabilities into it. I'm not sure.
Okay. 16. Okay. Which band is used for Earth observation? Yeah.
That really depends on what you're observing. So I think the two companies I was talking about, they are using probably X-band, most likely X-band, because they are basically just doing imaging of Earth. But if you're using synthetic aperture radar for science, they will be looking at different frequencies that can range from maybe even UHF. I know there is a lot of work being done at S-band, L-band at JPL for deformation, deformation of the ground. And I don't know, probably Ku-band, K-band, and I haven't heard of anything above that frequency, but it could be. I'm not sure.
Okay. I think we have two more questions. Sorry, yeah. How do you take into account the effects of wide temperature variation in Martian environment on the stainless steel antenna of the Mars rover?
Yeah. So the rover antenna is not stainless steel; it's aluminum. The antenna on the Mars helicopter is made of stainless steel, and the reason why it's because the wire was so tiny that because of vibration, it would have gone crazy if it was not stainless steel. So stainless steel is very, very, very strong. So it's very, very stiff and allows us to survive all of the environmental levels, vibration, shock, and all these things. So that's the reason why. Temperature, like I said earlier, it's just CTE. So the stainless steel will have its own CTE. I think stainless steel is actually pretty low CTE. So the variation is going to be very, very small.
Okay. Yeah. Last question, Nasir. Yeah. What is the general advice you give to young scientists that intend to pursue a career in space antenna engineering? Could you give some key points? Okay, this is like a very good conclusion for all the attendees. Please.
Yes. So, yeah. That's a very good question. The only advice I can give, and I give everyone I know who wants to be good at what they do in general, it's not just antenna engineers. You need to be extremely curious. You need to learn a lot. So even in your field, I mean, most of PhD students, they work in a very, very specific niche, but there is much more to that. So read other papers, read books. There is a lot of very good books that you can read where you will learn a lot of things, even like the way of thinking or engineering approach and all of that. Those are the books I like the most, and those are the books that I was reading when I was a student, as much as I could. I was much less of a fan of the book that only are how do you call that, test book, which is just theoretical. I really like the books. I don't know if you guys know Professor Zini Cheng. Professor Zini Cheng, he wrote a lot of books that are extremely practical, where you can learn how antenna works and how to sync, how to design an antenna from scratch when you have requirement. And those are some of my favorite books to advise students or young engineers to read, because you really get into this mindset of an engineer, and that's really what you need to acquire. You have two ways to acquire that. The first one is to work, but it's going to take a lot of time, or you can rely on what others have learned who have many, many years of experience and absorb all of that within a few hours of reading over the weekend these books. So that's what I really, really advise you to do. Read as much as you can, and also work with others. When I was a PhD student, or when I was an engineer, I mean, when I'm still an engineer, I talked with my colleague. As soon as I have them, I talk to them. And that makes you much more efficient, because two things you get out of that. You teach them as well, because they're learning from your problems as well. And you're learning from them if they already had these problems before. So that allows you to get better much, much quicker. And that allows your colleagues around you to get better as well. So that's really what I advise a young engineer to do, is try to build this environment where you can share with your colleagues and learn from them, and teach them as well. From any ages, you can do that. I can teach things from senior engineers, and very senior engineer can teach me things. Because it's just based on what you work on. So that's the things that I advise. And then the other thing, as soon as you start working, you have the opportunity to expand yourself. So you're gonna work on an instrument, you're gonna work on an application. Don't be shy on asking questions, because people are always happy to share what they know and teach others. So be curious, ask questions. Why do we have this requirement? Where is it coming from? Why do we have this? I think if we did that, it would be much easier for me. Do you think it's possible? Ask these questions, because they don't know. They don't know what's easy for you, what's difficult for you. They don't know what you're capable of doing. So always ask where the requirement come from, and try to refine this requirement by working back and forth with them. So that's the advice I give.
Okay. All right. So thank you very much. I think that concludes our session. Thanks again, Dr. Nasir, all the way from France. Thank you very much to make this happen. I think we have been, well, yeah, something to show to you, a certificate of appreciation from us, from the faculty, and also from the IEEE. Thank you very much, Dr. Nasir.
Thank you very much.
Yeah. All right. So I think this will end the session. I hope all the attendees will try to be aware of our upcoming webinars, which is this one is the ninth series number 9. We will have another one, which is probably next week, or 2 weeks time. So just keep in touch and stay safe. Thank you very much, Dr. Nasir. Hope to see you again sometime in the future.
Yeah, likewise. Thank you for the invitation. It was my pleasure. Thank you very much.
Okay, thank you. Thank you, everyone. Assalamualaikum. Thanks.
Bye.
Bye then.